Hi, this is Andrea Hendricks. Welcome to Math 1111 Online. This is the first in many video lectures that you'll hear me give this semester. And if you ever have any questions on any of these topics, please feel free to contact me. The first lesson that we're going to cover is the topic of relations and functions. And what I always try to do is to get you thinking about these terms and things that you know from your everyday life. Certainly these have mathematical relations, but we also want to think about those things in everyday terminology to maybe help you see the connection with some things. So the first of those two terms that we're going to talk about are relations and functions. So if you were just to hear the word relations in an everyday conversation, what would you think of? I generally would think of relationships between people, right? Or relationships between different objects. For functions, what would you think of? If you think of something functioning, I think of something that functions properly or works properly. And I'll bring back the way that those two definitions mathematically are connected to these everyday definitions in a little bit. So the objectives that we're going to cover in this section are to review set builder and interval notation, to define a relation, find the domain and range of that relation, define a function, find the domain and range of a function, use a vertical line test, and also use function notation. This section, I'm sorry to say, kicks off with a bang, has a lot of key concepts that you need to be familiar with throughout the course, so especially those terms, domain and range. That will be something we probably revisit in nearly every section of the course. Our first objective, though, is one that you should be familiar with. That is set builder and interval notation. And I've given you several here just to remind you of these things. If you have any questions about it, please don't hesitate to contact me. But set builder and interval notation are different ways that we can describe solutions of numbers. And so, or solutions of sets, rather. If I have a number line with all the numbers to the right of 3 shaded with the parentheses on the 3, remember that parentheses means that that number is not included. And all the numbers that are to the right or that are shaded we can think of as the solutions x. So we're trying to find out how do these regions or this region of numbers relate to this reference number 3. We can write that in a set builder notation. We say that is the set of x such that, and then what is the description on the values of x? Well, in this graph, those values of x are all larger than 3, so we would write simply that inequality. A way we can also describe it is interval notation. Interval notation lists a number from the smallest or from the leftmost to the rightmost in the set. So we begin at this number 3, but we continue without bound to the right, which takes us into numbers like 100, 1 million, 10 million. It keeps going without bound, and we use infinity to denote that. Here's a second set that is starting at the -2 and shaded to the right. The difference is this one has a bracket. Bracket means that that number is included in the set. So if we think about how do these shaded numbers relate to this number -2, they are to the right of it, which still means that they are larger than -2, but we also put an equality part there because they are allowed to equal -2 because of the bracket. Interval notation is very similar to the first. We begin from the left at -2, continue without bound to the right, which takes us to positive infinity. The third example is all the numbers that are less than 0, right, because they are to the left of 0. And so we would say that these numbers x are less than 0. So that's where we get this set builder notation. The interval notation is reversed because now the leftmost number in this set are all those negative values, which go without bound to the negative direction. So that's from -infinity to 0. Again, using parentheses because we cannot include the 0. Notice also there's a parentheses on all the infinity symbols because we can never reach that number. A few more examples. One now that has a bracket and shaded to the left. These values that are shaded are less than or equal to 5, so we write the set of x such that x is less than or equal to 5. Denoted in interval notation from negative infinity, because that's our leftmost start point. Where does that end? And it ends at 5. These next two are examples of what we call bounded regions. And they are bounded because they are bounded between two specific numbers. They don't extend indefinitely to either the left or to the right. So these values of x lie between these endpoints, -1 and 5. So we write that in set builder as a set of x such that -1 is less than x is less than 5. In interval notation, our leftmost point is -1, our rightmost point is 5. Very similar for the next problem. We have another bounded region. The values of x lie between -7 and -2, and they are allowed to equal that because of the brackets. So we say that x is between those -7 and -2 by writing -7 is less than or equal to x is less than or equal to -2. And in the interval notation, it is from -7 to -2. The last one is an unbounded set. It continues indefinitely to the right and to the left, covering every single number on the number line. So we write this as the set of x such that x is a real number. The leftmost to the rightmost numbers are from -infinity to infinity. We're going to use these in how to write domain and range later on in this section. So now that brings me to our second objective, which is to define a relation. Relation, I had said before that relation reminds me of something about two people. It's where you have a relationship between two quantities, and the most general definition of a relation is that it is just simply a set of ordered pairs. And if you remember, ordered pairs are relating two values. We most commonly use x and y, but we are assigning a value y to that value of x whenever we write that. In other words, there is a relationship between those two quantities. A set of ordered pairs can be denoted in many ways. You can actually have a listing or a specific set that's given to you. Those can also be given to you in a table or a graph, or implicitly in an equation. And we'll see those all as we go through this section. I've given you one on this next page where I think is something that is just probably more interesting than just giving you a set of numbers that have no meaning. But this is the cost of advertising for a 30-second Super Bowl spot since 1996 all the way through 2006. In some of my research, I found that back in 1967, the cost for a 30-second Super Bowl spot was only, I say only, $42,500. And that was on CBS. I found also that it used to be shown on two different channels, CBS and NBC, but we'll just go with the one there. And I've also read that this year CBS is wanting $2.6 million. Can you imagine that? For a 30-second Super Bowl spot. But do you see there is a relationship between these numbers? First of all, what are the numbers? Well, we have a year and we have a cost. And so we can write that as an ordered pair. And the listing then of all these ordered pairs would make up a relation. So if I wanted to write the relation that was being described here by this table, I would have a lot of ordered pairs. And I may not necessarily write out every single one of these, but just so you get the idea, we would have 1967 paired with the 42,500. And you know what? I should write that in terms of millions of dollars. If we divide that by 1 million, I believe, if my math is right, 0.0425. Okay. Then we have 1996 corresponds to 1.37 million. 1997 corresponds to 1.46 million. 1998, 1.56. You see, so all I'm doing is writing the ordered pairs that correspond for each year that I have on my table. What are we up to? 1999 corresponds to 1.87. I'll do a few more of these. 2000 corresponds to 2.38. 2001 corresponds to 2.26. 2002 corresponds to 2.06, so we had a decline there. 2003 corresponds to 2.22 million, and so on. I'll do ... and then we'll end with 2008 corresponds to 2.6 million. Okay? So this is a relation, just that set of ordered pairs. Again, I chose this because there's some meaning behind those numbers. But more importantly about a relation, we can define two other terms called the domain and the range. The domain of a relation is simply the set of x values of all the ordered pairs in that relation. So in this relation that I've described here, the set of x values for me would be just simply the set of years that I used in my table. So it would have 1967, 1996, 1997, 1998, you guessed it, every single one up through the year 2008. Okay? Now range is the set of y values. So if I were to explicitly list all the y values from this relation, I'd have 0.0425, 1.37, 1.46, 1.56, 1.87, 2.38, continuing on, what is that, 2.26, 2.06, 2.22, 2.25, 2.4, 2.5, and 2.6. Okay? So domain is x, range is y. If you need a way to remember that, think of that in terms of alphabetical. Right, x comes before y, and d comes before r. So that's how we get those paired up. Now, for our next objective, let's just practice finding the domain and the range of some relations. So I here just have some that probably don't mean anything to you, and that's fine, but just to get the idea of here's a set of ordered pairs, that is all we need to define a relation. Think about the domain and range of those. So in this first example, my domain is just simply, and I'll do D for short, the set of x values from that listing of ordered pairs. So I have a -2 as an x value, -1, 0, 1, 2. My range is a set of y values. So I have 4, 1, 0, 1, and 4. Well, I've already listed the 1 and 4, so I don't need to write those again because it's just a set of numbers, so they don't have to include all the repetitions of those numbers. My next example is listed in this chart form, but here I still have ordered pairs. If you wanted to, you can certainly write them out in the ordered pair format. You don't have to do that. So what is my domain? My domain is my set of x values. Well, I have -2 for x, -2 for x, -2 for x. So only write the -2 because that is just saying that that's the only x value that was used in those ordered pairs. My range is a set of y values, which is 5, 4, and 0. Okay. So far we're not doing anything with those, we're just trying to define what they are. This is called a mapping. So we're showing a relationship from this first set to the second set, and that's denoted by these arrows. So again, as an ordered pair, we're saying that -3 corresponds to -5, -1 is corresponding to 4, and 3 is corresponding to 8. That's my relation. In other words, that set of ordered pairs. So my domain of that relation is the x values, which is -3, -1, and 3. My range, the set of y values, -5, 4, and 8. Okay. So we've seen a listing, we've seen a mapping, we've seen a table. Well, I can actually have an equation, and from an equation I can come up with a graph. And if I wanted to graph an equation, remember that you just plug in values for x and solve for y. If y is equal to the opposite of x, I'm just going to find the opposite of these values to obtain y. So if x is -3, y is the opposite of that, which is just 3. The opposite of -2 is 2. The opposite of -1, 1. The opposite of 0, 0. The opposite of 1 is -1. The opposite of 2 is -2. I could stop there, but remember x could be anything, so this is just a listing of a few ordered pairs, but I graph it to get the whole set. So let me graph this for a minute. -3, 3. To the left, 3 up, 3. -2, 2. -1, 1. 0, 0. 1, -1, and 2, -2. So if I graph this, kind of hard to do on a computer, but you can get the idea. That is my relation. So this relation is made up of infinitely many ordered pairs. Do you remember that? That on a graph of a line, there's infinitely many ordered pairs. In the previous problems, I only had a finite set. Finite means countable or specific number, right? So for infinitely many, this goes on without bounds. So I would think that my domain and range then would be infinite sets. So this is where my set builder and interval notation come in. My domain and range of this graph are what are all the x values on this graph? What are all the y values on this graph? Well, all the x values are going from which direction? From the left to the right. You have to visualize this, okay? These are points that consist of the x and y values, but I've got to extract out what are those x values on the graph. So the way we do that is kind of think about superimposing this to the x-axis. Think about what values of x were hit. When I did that, if I dropped every point down to the x-axis, do you understand that that would cover the entire x-axis? And it would continue without bound to the left and to the right because of those arrows. So we say our domain is all real numbers, or -infinity to infinity. My range is if I could superimpose these points to the y-axis, right? So think about drawing every value over to the y-axis. What would I get? I would have this whole number line covered, right? If I flatten that out, it would cover it. And again, my arrows indicate that that goes on and on and on without bound. So my range is all real numbers. Okay? So you're extracting out from those points. If I could label every single point on my graph, what would I have for my x values and y values? Well, I can't label every single point, right? I mean, there's a point everywhere. I can't do it. It continues forever and ever and ever and ever and ever. Okay? So it covers every single value that I could ever think of. Here's one that I don't have the equation for. I could have given you the equation, but I was just trying to get you to understand reading from the graph. The same concept of reading from the graph to find the domain and range. So the domain is a set of x values from this graph. Well, let's see what this point is here. what is that? Negative 1, 2, 3, 1, 2, 3, 4, negative 3, 4. I've got some x-intercepts, but that doesn't really matter because the graph goes on beyond those, but we can label those as negative 1, 0. And what is this? Negative 5, 0. Okay. My y-intercept, if I have this drawn to scale, is 0, negative 4. Okay. But the arrows are critical here because it denotes that we're going on and on and on. So again, I want to kind of superimpose all these points on my graph. If I could flatten this out and get it on top of the x-axis, what would I have? Right, for every point on the graph, there's a point down to the x-axis that that goes to. So if you kind of put this up here and put this here, because I wish you could see my hands, I'm just flattening this out so it touches the x-axis. What points would be covered? Well, because of the arrows there, it goes on and on and on from negative infinity to infinity. Now, to do the range, I'm going to do a similar thing, except that it is going to be from, don't want to erase all this, I'm going to mess it up. My range is going to be finding the values that are on the y-axis. So if I could kind of flatten this over and think about what values of y are covered from this graph. Right, all these points are going over to the y-axis and it continues without bound down there. Now here, notice that there is a distinct point where it ends. So we read the range from the bottom up because we're doing it from the smallest to the largest. Well, this continues without bound in a downward direction, so that's from negative infinity to the topmost point. Well, my topmost y value is 4 with a bracket because that point is included there. So domain is read from left to right because we're reading the x values, and the range is read from bottom up because we're reading the y values. Now let's think about this next objective, and that is to define a function. A function is really just a special type of relation. A function is a relation in which each element in the domain corresponds to exactly one element in the range. You're saying, what in the world does that mean? Well, think about it like this when I said before that a function is something that works properly. It basically means that the x value can only be mapped to a one y value. It's kind of like going to a vending machine. And if you push a Diet Coke button, you want that to go only to the Diet Coke, right? You don't want that to go to a Diet Coke or a Sprite. You don't want to have two things coming out from that. So you want that Diet Coke button mapped exactly to a Diet Coke can, right? So we're thinking about a function, a relation that works properly. My input, my x value, only corresponds to one y value. Here's another way to think about it. If I have a cell phone number connected to a person, when I type in that cell phone number, how many people do I want it to go to? I want it to go to just one person, right? That would be a function. Functions are actually used in everyday life. What about your GPC, your student ID? If I'm at the computer registering you for classes, the first thing I need is your student ID. Well, if I input your student ID, you better be the only person that is assigned to that. That is a function. Same thing goes with like your social security number and so on. Okay? So every x corresponds to exactly one y value. And we call x in this case an independent variable, and y is called the dependent variable, and that is because our value of y depends on the x. The way we can represent those, many different ways. We can talk about equations, graphs, tables, mappings, and also give some verbal descriptions, kind of like what I was just doing before with the student ID and the cell phone number and stuff like that. And from these, you're going to need to be able to find the domain and the range. So remember, a function is really now, let's review this, It is just a set of ordered pairs where each x value has only one y value. Okay? In other words, in your ordered pairs, in your list of ordered pairs, your x values cannot repeat. Because if it did, that would be an x value that has two different values that it's going to, or more than two. So we'll get through some of these representations in just a moment. Let's look at these problems here where we have to find the domain and the range. So these are representations that are given by equations, but from this equation you can actually get a table. From the table you can get a list of ordered pairs, and then from that you can get a graph. So if I have the equation y is equal to 2, to remember here to find that listing of ordered pairs, do you remember this is a specific example of a line? It's a horizontal line where y is always 2. X can be whatever you want it to be. So if I graph that, I would plot 0, 2, 1, 2, 2, 2, and say that it's all these points that line that horizontal line. Well, what is my domain? My domain goes from left to right. It is negative infinity to infinity. Now what is my range? It's better to see the range from this listing of ordered pairs. My range is only this number 2, right? Y can't be anything other than 2, or it wouldn't satisfy that equation. So my range is just simply the set consisting of the number 2. And that is a function because every x goes to only one output value. The output values happen to be the same, but that's okay. But you can't have an x going to more than one output value. Y is equal to 4x minus 1. Likewise, we could make a table if we need to, or you can use your slope-intercept form. But if I plug in the value 0, 0 minus 1 is negative 1. If I plug in the value of 2, 4 times 2 is 8, minus 1 is 7. So I can get a graph here, 0, negative 1, 2, 7. We're just going to estimate there. But the main thing is the domain, right? If I superimpose that down to the x-axis, it keeps going forever and ever and ever, and all these values are covered. So my domain is negative infinity to infinity. What is my range? Well, if I superimpose all those to the y-axis, all of these values of y are covered. So it's from negative infinity to infinity. You can use your calculator also to get these graphs if you need to. Y is equal to x squared minus 4. If you put in negative 2 and 0 and 2, just to get some examples here, negative 2 squared is 4, minus 4 is 0. If you put in 0, you would get negative 4. If you put in 2, 2 squared is 4, minus 4 is 0. So you have negative 2, 0, 0, negative 4, 2, 0. If you remember, this is a graph of a parabola. My domain, superimpose all these points down to the x-axis. Everything is covered. Domain is negative infinity to infinity. My range, superimpose these points to the y-axis, right? And all these points come over to the y-axis. Every point is covered from this bottommost point of negative 4, so it's from negative 4 to infinity. Okay. Now, how do we know these graphs are functions? You can do a test called the vertical line test. And if you have a graph, we know that it's a picture of a function if every vertical line drawn through the graph intersects the graph in no more than one point. Here is an example, like of this linear function here. We know it's a function based on what we looked at before. Every x has only one output value, but the vertical line says if I draw any vertical line down through that graph, the vertical line can't hit more than one point on the graph. Well, it's only hitting one point on the graph. So this is a function. We say it passes the vertical line test. Well, if I have this as my graph, a circle, and I do a vertical line through it, notice how the vertical line touches 2 points, so this is not a function. It fails the vertical line test. That's because every value on a vertical line has the same x value. So this is 2 points with the same x value. Let's say 2, 5, 2, -5. I'm just making up what those exact points are. But they are points on this relation, right? The relation is just a set of ordered pairs. But this relation has a value of x, that is a value 2, that has 2 different output values, so it's not a function. Now, function notation is a way that we can evaluate functions. We write it as, this is the way we used to say it rather, y is a function of x, but mathematicians always are lazy, so they invent symbols for that. So this is where we came up with writing y is equal to f of x. So this is read y is equal to f of x. Okay, it doesn't mean times. It means that the value of y is depending on the value of x. So here's an example. If we have the equation y is equal to 4x minus 1, we can write that in function notation as just f of x is equal to 4x minus 1. Now if we want to say find y when x is 0, in function notation we can just simply write find f of 0. So f of 0 would mean to let x take on the value of 0 and simplify that to find out what the output value is. So this would be this, 4 times 0 minus 1, which is just simply 0 minus 1 or -1. Find y when x is 3 means to find f of 3, which again is just to replace the value of x with 3. Oops, let me write that over again. So we'd replace in our function f of 3 would be 4 times 3 minus 1, which would be 12 minus 1 or 11. Okay. If I have f of t is equal to 3t squared minus 4t, and I want to find f of 3, I'm going to replace my t with 3. Okay. So I'd have 3 times 9 minus 12, or 27 minus 12, which is 15. Okay. So whatever number is inside parentheses is just the value that's going in place of the variable. That's all you do to evaluate a function. Now the last thing we need to do is to use a graph to find function value. So I've just given a graph here. And if I want to find f of 0, understand what this means. 0 is my x value. So this is really trying to tell me to find on the graph what point where x is 0 lies on the graph. 0 what lies on the graph? Well, here's my x value 0. Here's a point on the graph. It looks like 0, 2. So if 0, 2 lies on the graph, we said that f of 0 is equal to 2. So f of 0 in layman's terms means what is the y value when x is 0. Okay. What about f of negative 4? This means what is the y value when x is negative 4? Well, here's negative 4, right? Negative 1, negative 2, negative 3, negative 4. If the point happens to lie there on the x-axis, that is the point negative 4, 0. So we would say f of negative 4 is 0. So f of negative 4 means what is the y value when x is negative 4? What about f of negative 2? Negative 1, here's negative 2 on the graph. What is that? Negative 2, 1, 2, 3, 4. Negative 2, 4. So we say f of negative 2 is equal to 4 because the point negative 2, 4 lies on the graph. And one last one, what is f of 2? Well, here's f of 2 because it is 2, 0. We know f of 2 is 0 because 2, 0, oops, lies on the graph. Didn't mean to do that. Okay. So one more, f of 5. F of 5, go over to the right on the x-axis, right? Understand that's where I'm always starting. I find 5 on my x-axis, and then I go down to where it's connecting to the graph. 1, 2, 3, 4, 5. Go down. F of 5 looks like it is negative 3. Okay, so I find the point in parentheses on the x-axis. I have to move up or down to connect with the graph, and then read off what y value is there. Okay, so this was a lot of material in this section. If you have any questions on this, please don't hesitate to contact me, and I'll also make a video where I'm just working problems so that you can see more of these worked. Okay, thank you.